Hello everyone, welcome to my talk on how to build rollups on Bitcoin. A little background on me, our host already told you, I'm a co-founder and CTO at Chainway Labs. We were previously known on our work for proof of innocence on Malloc privacy pools and Railgun. Now we are working on Citria. Citria is a ZK EVM rollup on Bitcoin, and it has a two-way peg bridge program called Clementine. But before going into how to build these rollups, why do we even need rollups on Bitcoin? Well, just like Ethereum, the first reason is scaling. Here you can see a picture we've taken from mempool.space, one of the most popular Bitcoin explorers. And all the blocks are full. There are multiple blocks worth of transaction waiting in the mempool, so in the queue basically. And a simple Bitcoin transfer with medium priority is about $50. So this doesn't scale, right? So we may need more throughput and shorter block times. That's what we call scaling Bitcoin. Well, the second reason is, surprisingly, it's scaling again. But this time it's a bit different. It's about achieving more with transactions. So when you look at Ethereum rollups, for example, Arbitrum, Optimism, you can do the same things as L1, but for cheaper, but maybe faster. But in the end, you're using the same apps, right? That's not the case for Bitcoin. On Bitcoin, you have Bitcoin script, a stack-based minimal programming language that tells you how an input can be spent, basically. And in this language, you're very limited. You can check for certain signatures. What I mean by certain is you can check for signatures only for certain serializations of the transaction. So you can't check for anything, basically. You can hash some bytes, that's useful, and you can add and subtract numbers. But you can't multiply numbers, so that rules out a lot of stuff, right? Makes it infeasible to do a lot of math. You can't concatenate bytes, so you can't do, for example, Merkle-proof verifications. And I think most importantly, you can't enforce properties of transaction outputs. So this is called covenants in the Bitcoin world usually. And what does that mean? Imagine I send my friend 2 Bitcoin, but I have some conditions. I say to him, either you spend this 2 Bitcoin by sending to some address A, or you send to some address B. There is no such mechanism in Bitcoin to enforce the next spending path of the funds. So that means you can't actually build any kind of useful smart contracts inside Bitcoin. And that's very important. So our proposed solution is building rollups. In order to build rollups, we'll need to do 2 things. We'll need to use Bitcoin for DA, and we're going to use Bitcoin for settlement. Okay, so, sorry. Okay, my clicker didn't work for a while. So let's first inspect how to, use Bitcoin for DA. So in Ethereum, when we want to put arbitrary data on TD-L1, we have the call data and we have the blobs, right? So where can we put the data on Bitcoin? A Bitcoin transaction is fairly simple. There are inputs. So Bitcoin is a UTXO-based blockchain, right? What does that mean? That means a transaction has inputs and a transaction has outputs. These inputs are actually outputs from previous transactions. So whenever you make a transaction, on the output, you specify how this UTXO can be spent. So while you are spending those UTXOs, then you're going to provide what needs to unlock those UTXOs. So here are the list of input and output fields in Bitcoin transactions. And there is 2 fields you can put arbitrary data without breaking anything, without making your transaction invalid, so one is the witness field in the input and the locking script in the output. This is usually called script pub key, but I think locking script is a much easier to understand name. And so, with these two fields, the locking script and the witness, we have two common ways of putting data onto Bitcoin: the op return outputs and witness scripts. Op return outputs are fairly simple. Basically, when you're locking your UTXO, you use OP code return, so op return, first, so that whenever that locking script is executed, the execution of the program returns early, right? So that output can never be spent. So that's what we call provably unspendable. Well, we like this property of op return outputs because in our nodes, we can delete these UTXOs and we don't need to store them, right? But there is a problem with op return outputs. You can only push 80 bytes. And you may ask, why? A transaction is limited with 80 bytes maybe? No. When you look at consensus rules, you can make your Bitcoin transaction as big as the block itself, so 4 megabytes. But there are certain limitations in Bitcoin nodes that specify when that node is going to propagate some transaction or not. So these limitations are actually a bigger set than consensus rules. So op return outputs are normally limited by number, so you can only have one op return output per transaction. You can only have op return outputs with 0 values, and you can only push up to 80 bytes. Very weird, but it makes op return outputs unusable for bigger data. So here's an example of op return transaction. Basically, funds come in, funds come out, and here you have like the op return output with 0 values. So the second way of pushing data on Bitcoin, the witness scripts. Witness scripts are introduced by an update, a software called SegWit. And this type of putting data on Bitcoin became popular around 2 years ago with the launch of a protocol called Ordinals. Ordinals was a way to inscribe images, videos, audios onto Bitcoin itself and basically creating NFTs, right? In these scripts, you have something called an envelope, which pushes OP false onto the stack. And with the OP if right there, you directly consume that OP false, and you never execute the inside of the if block, right? So that means you can do anything inside of if, the if block, and your transaction will be valid. Due to the way how SegWit works, this part of the transaction, the witness field, is priced at 4 times cheaper than any part of the transaction. So this is actually a very cheaper way to put data on Bitcoin. And it caused big trouble because ordinals, people went crazy with ordinals basically. They started putting 4 megabyte images on Bitcoin. So anyway, so Bitcoin maxis don't like this. That's why I said cause big trouble. So, so we went over how to put data on Bitcoin, right? We needed to put data on Bitcoin to create rollups. If you know how to put data, you can process all the transactions in a block and, you know, try to extract data, but that's consuming a lot of processing power, right? If you're going to make any kind of ZK proving, or let's say you want to have very small nodes for your rollup, you want to distinguish, you want to have an easier way to extract data from your DA layer, being Bitcoin. In Ethereum, for example, you could just filter for transactions that happened against a smart contract. You can listen for events of some certain signature. On Bitcoin, you don't really have that. You'll have to look at the transaction bodies of all the transactions in the block. So what we do is we created a notion of relevant transactions. And we defined relevant transaction as having WTX IDs. So that's the transaction hash basically, with certain prefix. You use some extra bytes in the transaction, and you try to mine basically a transaction that has a certain prefix. So that way you can have namespacing on Bitcoin. So We now know how to put data on Bitcoin. We know how to distinguish that data from other transactions. Now, okay, what do we do with this DA layer, right? So in order to build your rollup, there are a lot of constructions, of course. So I'm going to talk about what we do at Citria. In Citria, there is two types of data put onto Bitcoin right now. First one is sequencer commitments, and the second one is batch proofs. The sequencer commitments, I think some of the Ethereum ZK rollups have a similar notion like this, is used for faster finality for full nodes. It's a small commitment to some block range, and the full nodes seeing those data, if they're syncing over the L2, they can now say, okay, we have a valid commitment, there's going to be a proof for that, and it's going to finalize. So it's some kind of finality between the L2 and L1 level finalities. And then you have the batch proofs. We use Restore Groth 16 proofs for our execution of block ranges. And in those ZK proofs, we output the state diff of the rollup so that our rollup state can be reconstructed from L1. We use state diffs instead of full transaction data because Bitcoin's DA is not, it is a little bit limited, right? 4 megabytes every 10 minutes. And we experimented a little bit and found out, you know, state diffs are a smaller way to put your data on Bitcoin. So a little trivia here. Right now, Citria testnet sends about 2 megabytes of data every day to Bitcoin testnet 4. So that's about 0.3% of testnet 4's block space. Okay, we went over how to put data on Bitcoin, how to distinguish data on Bitcoin, and what to put on Bitcoin, right? We pushed a lot of data, 2 megabytes every day, and what are we going to do with it now? There's no smart contract on Bitcoin, right? You can't really track the state of the rollup. So right now you have a sovereign rollup, by the way, as some people define. What we're going to do now is we're going to create some light client logic that is bound to the Bitcoin L1, which means it scans for Bitcoin block headers, checks for proof of work validity, and then extracts the transactions inside your Bitcoin blocks, and it will check for only the namespace in the Bitcoin block and scan for sequencer commitments and batch proofs. You're going to have some kind of state tree accessible to your light client proof, and then you're going to start saving information about these batch proofs and sequencer commitments, and with some certain algorithm you define, you're going to decide what the state root of your rollup is. So that way, given a Bitcoin L1 block hash, you have the state of your rollup. And that's very useful information. So, we said in the beginning of our talk, we wanted to have a settlement layer to Bitcoin so that we can be a proper rollup, right? So, how are you going to verify your light client proof, right? I guess you could build a Bitcoin script that verifies these proofs, but experimentation shows that building a Groth 16 verifier in Bitcoin takes about 800 megabytes. Even if we could fit that into a Bitcoin block of 4 megabytes, UTXOs don't know about state. So you're not going to have something like, okay, my rollup state root was A. In this block, I processed something, and now state root is B, right? That's not going to happen. I mean, even if somebody solved that for you, then you don't have covenants, right? You can't enforce, you know, upon verification of something, I'm going to let user withdraw or not, right? So until we have an enshrined covenant solution on Bitcoin, there isn't going to be trustless bridges. So what about trust minimized ones? Well, that wasn't possible until very recently, until BitVM. BitVM came out about like 1.5 years ago. It's a very new solution. It uses pre-signing of a predetermined transaction graph among n parties to create the notion of covenants, and it has a native way to verify Groth16 proofs, but BitVM uses that only on the pessimistic case because it's still very expensive, right? Because remember your Groth16 verifier took 800 megabytes, right? So how does BitVM achieve that, right? The Groth16 verifier part, I think, is a bit easier. You chop up your Groth16 verifier into chunks that can fit into Bitcoin blocks. And whenever there is a challenge, right, the challenger forces the operator, let's say, right, the challengee, to commit to start, end, and intermediary steps of these functions. And remember, we had the notion of covenants in BitVM, right? We pre-signed a lot of things, so you can force participants. Now, if the challengee can provide correct Groth16 proofs, the challenger cannot disprove anything, and it loses its stake. If the challenger can disprove the challengee, the challengee loses its stake, right? So you have an optimistic verification on ZK proofs. So now that we have something that can verify Groth16, or like, it can be Starks, by the way, it doesn't really need to be Snarks, but it's useful. Now that we have something that can verify ZK proofs on Bitcoin, now it's time to actually build something that can verify your rollup and that can act as a bridge. So that's why we are building Clementine. Clementine is a Bitcoin-based bridge, sorry, BitVM-based bridge between Bitcoin and Citria. And it uses BitVM to verify the ZK proofs, and it has its own transaction graph that allows for the covenants. There are 5 different parties, 5 sets of parties on Clementine. Of course, one is users, and the others are operators, signers, challengers, and watchtowers. Operators are there only to prepay for withdrawals, and they do this for profit. So whenever somebody withdraws from the rollup, they pay upfront and they get reimbursed later on. Signers are there to keep the funds safe. So it's an N-of-N multisig that signs some data and some transactions when there is a deposit done. And whenever there is a deposit done, they are also signing the necessary transaction graph for the withdrawal itself. So they only need to be online when there is a deposit, and the rest you don't need to worry about. Even only one signer deletes their keys, then you have your funds secured. So it's one-of-n trust security. And then there is the challengers and watchtowers. They come handy in the pessimistic case. Challengers detects malicious activity on Clementine, and watchtowers basically, this is a very edge case. They provide Bitcoin header chain proofs for these challenges. Okay, we don't have much time left, so I'm going to make a very quick explanation over what goes on Clementine. So let's talk about deposit. Whenever there is a deposit done, so Alice deposits 10 Bitcoin to the N-of-N signer set, they pre-sign everything related to that deposit. So from the deposit to the withdrawal, the last part of the withdrawal, and you go to 2 different smart contracts on Citria, and then you show, so 2 different smart contracts on Citria, the most important one being the bridge. You show that there was a transaction on Bitcoin, and the N-of-N signed that. That way, the bridge contract mints you the CBTC, and you made your deposit done. There is another contract called Bitcoin Litecoin, but I'm skipping that since we don't have much time. And on the withdrawal side, things are a bit different. You start the withdrawal by burning your 10 CBTC. Then there is an off-chain auction among you, the user, and the operator set to fulfill that withdrawal. Because you're going to start with 10 CBTC, if nobody accepts, you go down to 9.99, 9.98 or whatever. And whenever operators thinks they're in profit, they're going to fulfill that withdrawal and give you the funds on Bitcoin. And they will be reimbursed by the transaction graph that was signed at the time of the deposit for those 10 BTCs. And what we have with BitVM is that, I'm going to skip the slides really quick. What we have with BitVM is we have 5 minutes? I thought we had 2 minutes. Sorry. Okay. So thanks to BitVM, this can happen, right? Whenever an operator tries to get reimbursed for a withdrawal they didn't fulfill, or they're trying to double spend, a challenger can come in and start a challenge process. And now, thanks to the pre-signing, they are forced to commit to those Groth16 intermediary values, and the challenger can disprove that there was some malicious activity so that they lose their stake. This is what Clementine actually looks like. Clementine is a big transaction graph, and this is what I'm talking about when I say pre-signing. I think we would need another talk to explain this, so I'm going to refer you to OpNext talk by Ekrem Bal, my co-founder, and I'm going to skip that. Skipping that also to take some questions. So why do all of these though, right? We now see Bitcoin treated as a passive store of value, and we think Bitcoin should be much bigger than that. Our solution aims to save Bitcoin from bridges that are basically 3 or 5 multisigs to other chains. We want to provide better self-custody for Bitcoin. For example, on Citra, you can have smart contract account abstraction, right? That's going to be a much better Bitcoin holding experience for everybody. I guess we don't have much time yet, so I can take questions if anybody has any.
Thank you so much, Esad. Yes, we'll jump right into questions. We've got a few. Let's go for the first one. How are the Yopcat data used as inputs for the ZK proofs? How are they handed over? I thought this data is inaccessible.
How are the Yopcat data used as inputs for the ZK proofs? How are they handed over? OPCat is not live yet, so you can't use it if that's the question. I'm going to open the questions right here. Sorry, can't really see. Oh, I can't.
Shall I repeat the question?
I don't think I get the. Oh, okay. I think, okay, so he's talking about provably unspendable and pruning, right? So that's only for if a node wants to delete that data. By default, they don't actually delete those UTXOs. And for you to use that data in another transaction, there is no actually way of linking, hey, look at this transaction and this output, there's going to be some data used in this transaction script. You're going to need to reprovide that data. So, yeah.
The next question would be, how do you increase the block time in the rollup?
Well, a rollup's block time is defined by the rollup builders itself. There's not any limitations whatsoever. We use 2 seconds block time. We could make shorter or longer, and that affects how many transactions we can process, making ZK cheaper or more expensive. Yeah, but of course the finalization is going to be defined by Bitcoin block times. So you get faster L2 blocks, but to actually make sure those transactions are finalized, you're going to have to wait.
All right, and one more question. How many transactions and MBs of data are needed to be posted to Bitcoin in the case of Groth16 proof challenge?
That's a lot of data, and I'm not sure, I don't have the latest numbers. Great explanation by our Devrel, Talip.
All right. I think we can squeeze one more question in if you want.
Sure.
What Bitcoin upgrade would you wish for?
I personally like the CTV plus CSFS, so check template, verify, and check signature from stack, because it opens a lot of possibilities related to covenants. It reduces BitVM costs a lot. It's basically a great addition to Bitcoin.